Okay, the final part of the chapter looks at graphs using logarithms. Why would we do this? Well, if you look at a graph like this, which clearly is displaying exponential properties, which we would kind of expect, okay, this graph could get kind of meaningless quite quickly. All the data could be sort of shoved up into an unclear way. Let me give you some examples. Something like this one down here, okay? And you can't really appreciate, for example, what happened between 1970 and 1980 here, because the scale is getting destroyed by the fact that the data is growing so quickly later on. And this is an issue if we want to try and understand the relationship here, if we want to do regression, where we sort of come up with a rule for this so we can predict things and so on. Or just visually looking at it and interpreting it, it's not very helpful. And this applies in lots of situations. So in science and economics, growth of a population like bacteria, energy from earthquakes, the Richter scale, social media, all this sort of stuff. We're going to be talking about data that displays perhaps exponential properties. That one there is the Richter scale, for example. So we can have exponential growth, but then we can also just have other growth that's not linear. This is a cubic graph. So this sort of has, well, it would have very quick growth as we would anticipate, but it's not the same as something like this. So it's not exponential growth. However, even with these as well, we can use logarithms to turn them into linear graphs, which are much easier to look at and to understand. So two cases then. One is we're going to have polynomials. So we're going to say polynomials. We're talking about when we have x to the power of n. Yeah. And the other case we'll do is we'll look at exponentials. So exponentials are going to be, they're normally written in this form, okay, when you've got x up in the power. Polynomials first then. So use your log rules. Log of y, log both sides, so base 10 here, okay? Log of the left-hand side equals log of the right-hand side. Nothing too groundbreaking there. Log of y equals, well, you can break this up. So log of a product, which is ax to the n, is the same as log of a plus log of x to the n. Finally, you can bring the n down to the front. So they've kind of done two steps in one in that part there. Okay, so what? Well, if we say that a straight line is in the form y equals mx plus c, and we compare it to what we've got up here, we've got any more here? No. Instead of y, our y is going to be our log y. Okay. What's the part that sort of is a constant? Well, a is just a number, so the number is going to be that bit there at the end. Notice the part with two letters is also the part with two letters here, so it's sort of like the gradient and the x part. And it'll be more obvious what's going on if I show you the graph. So log of y we talked about. Log of a is like the c value, so that one's plugged there. And log x is what we talk about instead of x. So because we would normally compare x against y, we'd have x going across the bottom and y across the top. But it's not x anymore, it's log x. So we just change it to log x. X becomes log x. So what's the n then? Well, what's the thing that goes with the x normally? It's the gradient, isn't it? So if you take logs for all of these pieces, some of them are just numbers, like log a is just a number. So it fits the form of c. C is just a number. Log x is going to replace x. Yeah, for your x-axis, you're going to be talking about log x instead of x. And n here, n is like your coefficient of your x. In other words, n is your gradient. So if you had polynomials to the power of 10 or 20 or 30 or something, then you'd have a very big coefficient in front of x, and you'd have a very steep graph. That's what would happen. You do not, I mean, it's a good idea perhaps to sort of remember roughly what the graph looks like, but you don't actually need to memorize this. You need to remember that a polynomial can be written in this format, and you need to work it through with logs. Exponentials then. Exponentials, we're going to do exactly the same thing here, but it's going to look a bit different. And it makes sense that it would look a bit different because x is not a power there, but x is a power here. The base in this case is just a number. In fact, I would recommend pausing the video and having a go with your log rules and breaking pieces up, and notice how this is going to be a bit different. So log of both sides to begin with. As before, we can use log rules on this part here. So it becomes log a plus log b to the x, and the x can go down to the front. So we get this one here. If we do our thing again where we compare to a straight line, y is going to be y, log a is going to be c, nothing new there then. Over here though we had log x, and over here we just have x. Well, what do you think your x is going to be? Your x is going to be your x, isn't it? So log b is the gradient on this one. And because we're still talking about x, notice that this graph has x on its x-axis instead of log x. The other parts though are actually the same. Again, you don't really need to remember that. You just need to remember how to write a general exponential and work it through, and you will get the right answer. So what do we notice about these graphs here? Well, they now fit the format of a straight line. So they're easier to draw, easier to look at, and easier perhaps to perform some kind of regression, some going backwards and some prediction on. Let's do an example. So we have a graph about population, which is P over T hours. Look, it's in there, isn't it? So step one, is it polynomial or is it exponential? Well, as we might expect for population, it's exponential because T, okay, is in the power. A and B will just be constants, okay? Some stuff is drawn for us already or talked about. So the gradient is 0.6 and that one there is 2, 0, 2, 2. So write down an equation for the line. Well, what are we going to do? We're going to take logs of both sides. So let's have a look at this one here. If I take logs of both sides, what am I going to get? I'm going to get log p. So in fact, let's do this one over here. So I'm going to get log p equals log a. And remember, I'm kind of jumping ahead here. We separate them. We'll get log b to the power of t, but we'll pull the t down, so I'll get t log b. So log a and log b, where have we got these values from? Well, log a was the same as the c part. Log a was the same as the intercept. So you can make log a equal to 2. Well, how do you find a? 10 to the power of on both sides means that you're going to get a this way. Write down an equation for this line. So are we jumping ahead a little bit? Write down an equation for this line. Yeah, I suppose we have jumped ahead a little bit. All they actually want us to do is sort of to remember the form first of all. But let's keep going because we're into the question. This will do part B anyway. So as we were saying, A will be 10 to the power 2, which is 100. Okay. Why is this important? Because yes, you could write the equation for the line, but often the questions will want you to talk about what A is and what B is. So we've actually just found what A is. Okay. We know that log A is 2. Why is log A 2? Because log A is the y-intercept in these graphs. Okay. We also know that gradient is 0.6. So 0.6 would be the thing that went in front of t. So we've done some matching effectively. We've said that 2 is the same as log A, which gives us this equation. We can do the same with B as well. So the gradient is 0.6, but if we work forward with our logs as well, we know that log B is also the gradient. So that means that log b is equal to 0.6. To undo the log, you could do 10 to the power of on both sides. So 10 to the power of 0.6, and you will get an answer like this. Why is that important? Well, because this equation here says p equals ab to the t, you could actually put the numbers in there now. So you could say it's 100 multiplied by 3.98 to the power of t. And it means that you could tell me the population if I gave you some value for t, or you could even go the other way around. So understanding that you're matching between a straight line and the result that you get when you work through the logs allows you to work out these values. Interpret the meaning of a. We did this earlier in the chapter. So when t is 0, this will be 1. This will be 100 times 1. A is going to be the initial size of the population of bacteria in this case. Okay, let's do another one. So this one involves drawing instead. So we get some information here. So R and P are our sort of X and Y this time. And there's big numbers. So this is why we might want to use logs. And what do we have? So the relationship is given by P equals AR to the N. So we could do log rules on both sides. Let's do that. So log P equals log A plus, well, the N will come down. So we'd have N log R. Draw a table giving values of log R and log P to 2 decimal places. Well, here's R and here's P. So you just need to log these and draw it in a table. Okay. Remember, there's no number underneath, so that means base 10. If you do that, you should get these values here. And what do you notice about these values? Well, the scale would be much easier to draw than this. You don't want to go up to 1,000,000 on a piece of paper. Plot a graph of log R against log P using the values and drawing a line of best fit. So you might remember that in our polynomial growth graph, we had log X at the bottom, which is R in this case, and log P at the side, which is like the Y. So we could sketch this log R against log P, and it won't be perfect, but you'd get a fairly straight line from this. Okay. What does this have to do with this? Well, you'll see in just a moment. Use your graph to estimate the values of A and N to 2 significant figures. Well, this is where we go back to this now. So we know that the y-intercept, which is about 6.2, let's say, we know that that's the same as log A in this graph. So you can do log A equals 6.2, solve this one. So A will be 10 to the power of 6.2. Which is your A. Why does it say estimate? Well, it says estimate because you're using your graph, okay? And there's a line of best fit. So there's sort of 2 reasons there. N, how could we find N? N is the bit that goes in front of log R. Log R is like the X. So the thing that goes in front of the X. What do we call the thing that goes in front of an X in a straight line? That's the gradient. So you'd need to pick some points here, your difference in y's divided by your difference in x. You'd need to get the gradient. And clearly it's going to be some kind of negative, isn't it, from the shape of the graph. So you would do n equals minus whatever this one is here. Let's take a look. So the gradient from the graph, something like minus 2/3. Notice that's your n already. You don't need to do anything with it. N is just n. So there's nothing to do with that one there. The A, so yeah, down here, we said A is 10 to the power of 6.2, which is about this. So it's about 1.6 million. So just make it clear at the end that you've got your A and you've got your N. So an interesting example there, because you sort of go about drawing it and then you make the connections, you make the matching, but you do that from using your diagram. So you should be able to go either way, from using log rules and matching doing some calculations and perhaps putting something on a graph or drawing a graph and matching that back to an equation. Okay, pause the video to have a go at one more here. And I recommend doing all of the questions from the exercise for this, which is 14. I would do all of the questions, is my advice, because it's quite hard to find more practice for this topic. So assuming that you've done that, they wanted you to plot t against log p. So you needed to do log of these values. So the top line was the same, log of the values underneath. This is an exponential model, ab to the t. A line of best fit is drawn. Determine the equation of the line of best fit. So this is going to be a straight line. So for the equation, you will need the gradient. So you will need to draw this one here. Find your gradient, around a third, something like that. C should be about 3 point something. And that tells you this one here. Now, how would you know? How would you know which bit's which? Well, you would do logs of both sides. Log of p equals log a plus t log b. Yeah. So if we did this one here, we would know, for example, where are we? We would know that t isn't logged. Okay. So t is what we would draw on our x-axis. We would get the gradient from here and then hence determine the values of a and b. We would be able to match them, okay? If c is this value here, well, c is the same as log a. So you say log a equals this value, you get your a. Gradient, what's the meaning of gradient? It's the part that goes with the t. So you set log b equal to your gradient, you work backwards to get b. Estimate something t equals 5. Well, when you find your a and your b, you can actually write them in. So you can actually say p equals 1403 multiplied by let's call it 2.1 to the power of t. Then you have a model that you can actually use. You can put a 5 there and you can find an answer. Okay, my recommendation to have a go at all of the questions for this section, please.